Hi, my name is Josh Freilich, and I'm an engineer at Pure Storage. Today, we're going to talk about optimizing hyperscale flash storage. My colleague Riley started this discussion with his presentation yesterday. Today, we'll review some of the challenges and go into more detail on some of the solutions. And please raise your hand if you have a question at any time. I don't want to wait till the end. Let's get started. So to set some context, let's briefly revisit production hyperscale storage deployments. There's no single standard, as no two deployments are identical, but there are common design patterns. Generally, these are massive scale-out distributed file systems, and these systems isolate bulk data from global metadata, where data itself is stored on dedicated data storage nodes. We're going to concentrate on these data storage nodes as they contain the majority of the storage capacity of the system, and we're specifically talking about optimizing capacity. These data storage nodes contain local object storage software and block storage media. And while all the objects themselves are immutable and append only like you would expect objects to be, but it's not full-fledged S3 object storage, it's a local object storage software. All clients use the same object APIs, but their workloads vary massively. Training a foundation model, operating a transaction-heavy database, and restoring from backup all have vastly different I/O patterns and performance requirements. A data storage node must handle these workloads in a reliable and cost-effective manner. So these nodes have extreme capacity, performance, and efficiency requirements. But TLC is expensive, and hard drives are slow, and both are small. So what about QLC? Hyperscale data storage nodes optimize the performance, cost, and capacity through efficient use of QLC. Of course, this begins with the SSD itself, so first we'll explore how high-capacity drives create new challenges in SSD design. These quandaries warrant novel solutions, which are fundamental to the methodology of DirectFlash modules. Discover how DFMs, co-designed with flexible host-based NAND management software, that's a mouthful, can scale more efficiently than traditional SSDs. The host software in turn presents highly configurable virtual block devices with standard block storage interfaces. Finally, we'll learn how hyperscale workloads make use of these virtual block devices and benefit from this architecture. Let's begin with large capacity QLC SSDs. Large capacity QLC SSDs create new challenges and areas for optimization in SSD design. Unlike hard drives, NAND flash does not support in-place overwrites. NAND blocks must be completely erased and programmed sequentially. So SSDs need an indirection layer to map from a host-facing logical block address, or LBA, to a physical NAND block and block offset. This map is part of the flash translation layer, or FTL, within an SSD. And each entry in the map is called an indirection unit, or IU. The key point is increasing NAND capacity creates more IUs, and more IUs requires more DRAM. Until recently, a 4K IU using 4 bytes of DRAM per entry was ubiquitous. Such SSDs have a 1024:1 NAND to DRAM ratio. However, that configuration can only scale to 16 terabytes of NAND. Beyond that, each entry must be larger than 4 bytes. The natural next size would be 8 bytes, but today's 150 terabyte SSDs would require 300 gigabytes of DRAM. I actually have a 300 terabyte DFM here, and it doesn't have 600 gigabytes of DRAM, I'll tell you that. So scaling the FTL map for large capacity drives has been a trending topic in the industry. The general solution has been to increase the IU size and maintain 4 bytes per entry. Today, 16K IUs are common in large capacity drives, and 64K IUs are on the horizon. Funnily enough, I wrote that line, 64K IUs are on the horizon, and then someone else said it in exactly word for word in a presentation today, and I kind of cracked up. However, there's a trade-off with increasing the IU size. Unaligned writes are a consequence of large IUs and are surprisingly expensive. For example, to handle a 4K write with a 16K IU size, the FTL must first read from the existing IU, modify the buffer to contain the new 4K, and finally perform a 16K write. These read, modify, write operations are actually a new dilemma, as previously the IU size was identical to the sector size. So unaligned writes were just impossible. And as drive capacities further increase, so must the IU size. But 4K writes aren't going anywhere. They're not going to disappear. And a write that's aligned to an IU size today could become a read modify write tomorrow as the IU size increases. So both the cost and the frequency of read modify write will only get worse, and this performance pitfall will prevent SSDs from efficiently scaling. Solving this problem permanently calls for a radically different approach. By designing a large capacity storage device from scratch, the solution can be far more efficient. And that's what we did with the DirectFlash module. The DirectFlash module, right here, or DFM, is a modern take on the design of an SSD. Current QLC DFMs are available in capacities from 18 to 150 terabytes. 300 and 600 terabytes are in development, and we're already planning for even higher capacities. The DFM is an efficient foundation for building hyperscale data storage nodes. But first, we must understand how it differs from a traditional SSD. Conceptually, a DFM is similar to an open channel SSD and leverages host-based NAND management. The DFM does not have an FTL and does not accept random writes. It doesn't have indirection units, garbage collection, or internal RAID. These abstractions exist in our accompanying host software, purpose-built for use with DFMs. As the host software maintains the FTL, we call it the HFTL. So the DFM isn't just a hardware design, it's a hardware and software co-design, and that enables some unique optimizations, starting with the hardware inside a DFM. Let's dive deeper into the hardware of a DFM and contrast it with a traditional SSD. An SSD needs to store the FTL map in DRAM. The size of the FTL map is directly determined by the capacity and the IU size. So an SSD has a minimum IU size and dedicated DRAM simply as part of its design. That's well before it's manufactured or deployed into a production system. DFMs offer much more flexibility as there's no FTL in each drive. Instead, the IU size and DRAM usage are late binding decisions made when configuring the HFTL. So DFMs need just a minimal amount of DRAM, and it's entirely independent of NAND capacity. Similarly, DFMs don't dictate an IU size, as the IU size is software defined in the HFTL and flexible. Late binding and software defined is crucial because there's no single perfect IU size. It's a trade-off. A large IU size reduces DRAM usage, but a small IU size reduces read, modify, write. DFMs provide the flexibility to pick and choose and do so with efficient DRAM usage. Of course, DRAM is not the only hardware resource. We must also consider the efficiency of NAND. You've probably noticed that competing SSDs are available with identical capacities. It's actually a surprisingly nuanced topic in SSD design. The design starts with the capacity of a single NAND die, which varies across vendors and generations. Dies are then packed into a NAND package, and an SSD is composed of many such NAND packages. The total number of dies and the die capacity determines the raw NAND capacity SSD. But the total number of dies isn't just an arbitrary number. There are constraints and trade-offs in the NAND topology within the SSD. A NAND package can only contain so many die, and it's cost efficient to fully populate the package. But additional packages can increase the total bandwidth, so there's a benefit to using more packages despite the cost. And bandwidth only scales linearly with packages if each package is uniform in capacity, as imbalances can cause throughput bottlenecks. So while an arbitrary die quantity is almost always possible, very few are actually optimal. And that's just the raw capacity. There's also internal overheads. First, there's over-provisioning. Raw capacity is over-provisioned with respect to usable capacity to allow room for garbage collection. Second is RAID stripe overhead. QLC packs 4 bits into each cell, TLC 3, MLC 2, SLC 1. So QLC has a higher bit error rate than TLC. So QLC SSDs need to write RAID stripes across NAND blocks to reduce the risk of data loss. So you have 2 overheads on top of the raw capacity, that gets the usable capacity, And with all these variables, it's quite surprising that competing SSDs have identical capacities. Surely it wasn't by chance and optimal for everyone. Instead, there's trade-offs within the SSD which are opaque to the user to arrive at this competing number. DFMs don't care about conventional capacities. They're optimized for the maximum capacity. The design starts with the maximum number of packages and dies per package, and this determines the largest possible raw capacity. We then uniformly scale down the dies per package or number of packages to enable lower capacities as well. Because the dies are always balanced per package, the DFM design is optimal at every capacity. And there's no internal overheads, as over-provisioning and RAID aren't part of the DFM. Instead, the HFTL sees 100% of the NAND capacity and can configure over-provisioning and RAID as needed. That's why DFM capacities like 150 and 300 terabytes are unique in the industry. They're optimized for storage density and cost efficiency without hidden NAND. And the DFM design is actually compatible with any die capacity. We have DFMs from multiple NAND vendors for every generation, and each is unique and optimized independently. The result is that the DFM is a better building block for a data storage node. It has lower cost and lower failure rate as it needs less DRAM. It scales higher and more efficiently as it has fewer design constraints. And its capacity is 100% available to the HFTL, where IU size, over-provisioning, and RAID are configurable rather than static and opaque. With this overview of the DFM hardware, let's move up the stack to look at the flexible host-based NAND management software. An FTL manages NAND for a single SSD. The HFTL manages NAND for an entire data storage node, which often has 24 or more drive slots. There are several fundamental advantages to this approach. The first is more efficient fault tolerance. A traditional QLC SSD using internal RAID has local protection against data loss. It can handle partial drive failures, such as uncorrectable bit errors and bad NAND die. But internal RAID won't help if there's a complete drive failure, which is inevitable at scale. Instead, the HFTL uses cross-drive RAID and protects against both partial and complete drive failures. So a data storage node with the HFTL has greater data durability. Of course, drive failures are not new to QLC SSDs. Data storage systems have been designed to handle drive failures since their inception, using additional levels of parity with corresponding overhead. But because the HFTL is more durable, the entire storage system now has excess parity. The storage system can reduce this overhead without sacrificing protection against drive failures because it's included at the HFTL. As a result, the total system offers enhanced durability and better storage efficiency. Efficient fault tolerance isn't the only benefit of cross-drive RAID in the HFTL. To be more specific, we must consider the data layout of a cross-drive RAID stripe. So RAID terms vary across the industry, and we use the terms stripe and shard. So I just want to walk through a visual representation of what we mean by those terms. With cross-drive RAID, a RAID stripe is a singular unit written as shards across multiple drives. Every stripe contains data in parity, and apart from RAID 1 mirroring, every shard is unique. So there's a stripe, and there's each shard. Additional stripes are added, continuing the pattern. Both traditional SSD systems and HFTL data storage nodes require cross-drive RAID for data durability. Recognizing this necessity, the HFTL is able to leverage cross-drive RAID as a means to increase the IU size without incurring read-modify-write. Oh, my thing did not go. In a traditional SSD system using cross-drive RAID, the natural IU size would be the RAID shard size. Thus, writing one RAID stripe creates one IU update in the local FTL in each SSD. But with the HFTL, the IU size can be the entire RAID stripe size. Accordingly, writing one RAID stripe is just one IU update in totality. A common RAID stripe width is 16. So So the HFTL enables a 16 times larger IU and thus uses 1/16 of the DRAM. This is a really important point. Independent of the I/O pattern, so whether it's large objects or small objects, or parallel writes or sequential writes, or any read, modify, write optimizations, the HFTL enables orders of magnitude larger IUs by pulling the FTL out of the device, instead managing a single FTL across many drives. Larger IUs are critical as DRAM isn't just a cost savings, it's an enabler for, saving DRAM isn't just a cost savings, it's an enabler for continued capacity scaling. Add to that the improved data reliability and storage efficiency, and cross-drive RAID in the HFTL is clearly a huge advantage. So we've talked a bit about what the HFTL is, but how is it used? The HFTL, question? The question was the DFM itself doesn't have DRAM at all, it's only a host-based FTL. So it does have some DRAM. It has a minimal amount of DRAM. It needs DRAM just to operate, right? But it doesn't have any DRAM for an FTL. It doesn't have DRAM that scales with capacity. It just has a very, I don't know the exact number, maybe it's a gigabyte or, it's a trivial amount that's independent of the capacity. So the HFTL supports thank you for the question. The HFTL supports a variety of interfaces and configurations. In this particular example, each data storage node has 24 DFMs and runs a modern Linux kernel. Each data storage node runs both our HFTL software and the customer's object storage software. And the customer's object storage software is an abstraction on top of standard hard drives and SSDs. So the natural interface for the HFTL is to provide standard block storage, and the logical interface is to the Linux block layer. The HFTL runs a single user space process and operates as a ublk server. Ublk is a framework for implementing block device logic in user space and exists as an open source driver in the Linux kernel. As a ublk server, the HFTL exposes one or more virtual block devices, and although the word server may suggest otherwise, these are local devices available to other processes running on the same data storage node. The customer's object storage software also runs in user space and accesses these virtual block devices through Linux. This software leverages IOU-ring for high performance and asynchronous read and write calls to the virtual block devices in the HFTL. And similarly, the HFTL uses IOU-ring for its internal read and write calls to the DFMs. And thanks to co-design with the customers, it's a zero-copy stack from the DFMs to the object storage layer. So the HFTL is highly efficient and capable of millions of IOPS. In fact, you can find several bug fixes and performance improvements upstream in both ublk and IOU-ring developed by my colleagues at Pure and our customers. That concludes our overview of the HFTL itself. Now let's look at the configurability features it provides. Another question? The question is, ublk can be used with normal SSDs. Yes, so ublk is just a driver in the kernel that enables you to write a process that runs in user space and exposes a block device through the kernel. So you could do, you can use whatever you want behind the scenes with ublk because it's just user space software. The question is, can you have a host-based FTL on normal SSDs? You could, but you would still also have an FTL within the SSD. Yeah. So for virtual block device configuration, it's important to understand that Hyperscale QLC is not possibly one size fits all. But SSD constraints often dictate a rigid IU size and over-provisioning ratio. Instead, DFMs and the HFTL are designed for flexibility and provide immense configurability. Let's start with configuring the IU size. The HFTL offers not only configurable IU sizes, but also simultaneous configurable IU sizes at per volume granularity. A key insight is that total data storage for small objects is a fraction of the total data storage for large objects. A scale-out system isn't going to fill exabytes of storage writing 4 kilobytes at a time. The majority of that write bandwidth is actually going to come from larger objects. But larger objects aren't going to entirely replace small objects, and small object performance will continue to be important. So let's have both. A natural configuration is to use high capacity volumes with large IU sizes and small capacity volumes with small IU sizes at the same time. This configuration provides a huge improvement over a static IU size, because a small IU size would require a ton of wasted DRAM to index the large capacity objects, but a large IU size would reduce the DRAM, but also would incur heavy read-modify-write penalties for all of the small objects. The HFTL gives the best of both worlds, minimizing the DRAM and avoiding the read-modify-write. But object size isn't the only differentiator. Another useful property is data temperature. Hotspots with frequent writes and deletes over a subset of the data stand out, even among high bandwidth workloads. GenAI workloads are a great example. Consider checkpoints with a high churn rate, as many checkpoints are ephemeral. The comparatively larger training data set is routinely updated, but much of its content is long-lived. And committing checkpoints requires extremely high bandwidth, even exceeding what QLC can sustain. How can we possibly use QLC for this workload? Well, QLC NAND can also be programmed in pseudo SLC mode. PSLC offers higher throughput, lower latency, more program erase cycles, and requires less power. There's a cost though. It's only 1 bit per cell, as it is, after all, SLC. So PSLC should be used intentionally only when a workload needs it. And the HFTL can do exactly that by enabling PSLC just for specific volumes. Effective PSLC usage has numerous benefits. Obviously, it increases the throughput for write-heavy workloads, which would otherwise saturate QLC. But a hidden benefit is that by moving such workloads to PSLC, more QLC throughput is available for the rest of the system. A similar opportunity to optimize exists with the over-provisioning ratio. The over-provisioning ratio is often overlooked, but critically important to the cost and write performance of a data storage node. The benefit of reducing over-provisioning is obvious, as it increases usable storage. But it comes at a cost. Garbage collection uses the over-provisioning space to accumulate overwrites. And the more overwrites GC accumulates, the less data it has to copy out. We call this copy-out factor GC efficiency, and it's the primary driver of the write amplification factor, or WAF. And WAF directly affects the sustained performance of the system. So reducing over-provisioning can reduce the overall performance of the system. It's a huge trade-off for a typically hidden value in the SSD. The client workload itself also directly affects GC efficiency. The worst case GC efficiency comes from purely random overwrites, and in this case, WAF is just a mathematical function of over-provisioning. But many workloads are not purely random. For example, objects written at the same time, or at nearby addresses, or of comparable sizes, can be likely to die at the same time. We call this locality of overwrite, and workloads with high locality can have highly efficient garbage collection. As an example, again consider the AI checkpoints. With a mostly FIFO lifetime and segregation from other QLC traffic using PSLC, the entire PSLC NAND block should die mostly at once. So GC can be highly efficient even with minimal over-provisioning. In fact, we can even make up the usable capacity decrease from using PSLC by reducing the over-provisioning. So it's a huge degree of freedom to be able to handle everything from maximum performance to maximum storage efficiency. And with high locality, you can get both at the same time. These are just some of the configurable areas of the HFTL. Let's also look at how it ingests data. So before we've talked mostly about sizing and optimizing, but now let's talk about handling writes by data placement on physical NAND blocks. This is a bit of a cartoon diagram with a lot of colors, so please bear with me. A traditional SSD forms superblocks using internal RAID across NAND blocks. But how many NAND blocks make up each superblock? how many super blocks are active at once? Will two parallel client object writes to an SSD land in the same super block? Or will they use multiple super blocks? What about serialized client object writes? How do they compare to parallel? And what if a large sequential object is broken up into several writes? Does it differ significantly if these writes are issued in parallel or serially? I'm not going to answer all those questions. I don't know the answers. The FTL knows the answers, and we don't have it. The sprawl of NAND blocks used to store bits and pieces of a client object is an important factor in modeling overwrite locality, but it's completely obscured in the design of a traditional SSD. The HFTL actually makes this configurable and easy to understand. Each volume is assigned a maximum write parallelism, where a single unit of write parallelism is a RAID stripe. Each RAID stripe is across DFMs using a single NAND block per DFM. The recommended option is actually to configure each volume with a write parallelism of just one. This minimizes the number of open NAND blocks in the volume and maximizes overwrite locality. We call these direct volumes because it's as if the client were writing directly to the NAND blocks. With direct volumes, it doesn't matter if objects are large or small, if the objects are split into multiple writes or are a single write, or if those writes are parallel or sequential. It just doesn't matter because the HFTL will always place them in the same NAND blocks regardless. And so each complete object will be striped over the minimum number of NAND blocks. So it's not just predictable locality, it's also maximal locality. Recall that with large IU sizes, unaligned writes are actually costly read-modify-write operations. And some amount of unaligned writes are inevitable, but a block device can attempt to minimize these costs. The general technique is to use write coalescing, to coalesce two or more unaligned writes when they have IUs in common. If the union of these writes is IU aligned, the read and modify steps are actually avoided entirely. But the write parallelism of a block device dictates its ability to perform such write coalescing. And a traditional SSD with high write parallelism does not offer a ton of room. When it receives an unaligned write, it's inclined to perform the write immediately in order to maximize throughput. Now, if it gets two unaligned writes simultaneously and they're in the same IU, they can be coalesced. Or if the queue depth exceeds the write parallelism and you have writes waiting in the queue in order to be handled, those can also be coalesced. But outside of those scenarios, the SSD is forced to make a trade-off. Should it handle an unaligned write straight away, maximizing throughput and minimizing latency right now, but eating the cost of the read modify write? Or should it wait and allow time for potential coalescing? It might be more efficient in the long term, but in the short term, you're going to have higher latency and lower throughput. What should it do? It's a challenge for an SSD as there's no clear optimal answer. And the high write parallelism makes this case unfortunately common because you're often below the maximum queue depth. As a result, the write coalescing of an SSD is limited and opaque. With direct volumes, we can often coalesce writes without a trade-off. How? Well, a data storage node maximizing write throughput doesn't want to let a volume go completely idle. And it won't just have a queue depth of 1, it will be several writes deep. But the parallelism is only 1. And the queue depth exceeds the parallelism. So you often have unaligned writes waiting in the queue, and those unaligned writes can be coalesced for free. So by minimizing the write parallelism, we also maximize its ability to do write coalescing. We mentioned write parallelism a lot. So how does throughput scale with queue depth? With a traditional SSD, it's again a bit unclear. Linear scaling is great for throughput, but it's bad for overwrite locality and write coalescing. However, sublinear scaling is not any better, it's unpredictable. So it's just another opaque trade-off in the SSD. With direct volumes, write throughput scales linearly with the number of volumes writing. Direct volumes are designed to be a building block for data storage nodes. Within the HFTL, the volumes are independent logical constructs, so there's no cost or overhead to creating more of them. There's a maximal possible write throughput, ultimately bound by power, but up to that saturation point, scaling is totally linear. And of course, exascale storage systems are necessarily designed to scale to a plethora of storage devices. So not only are direct volumes well suited for massive scale, but they also minimize WAF and read, modify, write by design. So now let's use these direct volumes to optimize a data storage node. First, we must understand the workloads on the data storage node. Let's take an example node primarily storing large objects via the local object storage. However, it's not just storing large objects, because storing large objects requires storing metadata in order to index those objects. So the large objects have large I/O sizes and have a high demand for capacity and throughput, whereas this local metadata has much lower capacity and throughput needs, but critically, it's using much smaller I/Os for each write. So even with just a single class of objects, this node actually produces two workloads with vastly different needs from storage. Well, the large object workload is naturally handled by HFTL direct volumes with large IUs. For example, with a 1 megabyte IU, these volumes require only 4 gigabytes of DRAM per petabyte of NAND. Obviously, that doesn't work for the metadata, which might have a 4K IU, but is much smaller in capacity. As a result, you have a total system which has been optimized for both without having either a single IU size. And this is just one example. You have multiple NAND modes, over-provisioning ratios, and RAID geometries, which can be used to optimize across a diverse set of workloads. Question? So let me just summarize the last point of the question. The question is, if it's all extremely large IOs, you need a ton of DRAM to handle it. Is that fair to say?
All of it is extremely small IOs.
So, sorry, yeah, all extremely small IOs, you need a ton of DRAM. Yes, so if it's all extremely small IOs, there's nothing you can do. If every write is a 4K random write, I mean, really you have two options, right? You either have a 4K IU and you have a ton of DRAM, or you have a larger IU and you pay a read, modify, write penalty. I'd probably rather spend the DRAM on it.
So that case, it still comes down to that 600 gig or whatever the number that you quoted.
Yes, so there's the 600 gigs for 300 terabytes. That comes with 8 bytes per entry. If you use partitions, you can cut that in half, but yes. Was there another question? No, there was another question. Okay, moving on. But WAF is clearly an important thing. We're not the only ones trying to do that, trying to optimize that. The industry agrees that FTL is missing the context necessary to reduce WAF, and that it's a problem we're solving. And there have been numerous standards over the years. Dan in the back here has worked on a lot of them, maybe all of them. Currently, the most popular is an NVMe feature called flexible data placement. FDP is designed to give clients control over the behavior of the FTL, and it's really powerful with an amazingly rich specification and a variety of configuration mechanisms. But to keep it simple, I'm just going to describe an example workflow, and I'm going to use generic terms. Again, sorry, Dan, I'm butchering all of your work. Clients first allocate a set of resource identifiers from an SSD. Within the FTL and the SSD, each identifier maps to a unique superblock. Clients then map each workload to an identifier, and for each workload, writes for that workload are passed the identifier along with their data to the SSD. And so if every workload gets its own identifier, the FTL segregates workloads into their own NAND blocks. Ultimately, the goal of FTP is to maximize write locality, improve garbage collection, efficiency within the SSD, and lower WAF. Dan's not kicking and screaming, so it can't be that bad. This should sound familiar, as the HFTL was actually designed with FTP in mind. HFTL direct volumes similarly segregate workloads and offer control over data placement. Rather than mapping workloads to allocated identifiers, clients simply assign workloads to a volume. These control mechanisms are similar, but the HFTL has a fundamental advantage in its architecture. the HFTL is coordinated over multiple DFMs, whereas FTP operates within an individual SSD. This creates a distinct overwrite locality advantage for the HFTL. Each SSD would have its own FTP instance, which isn't synchronized. That means each SSD has its own FTP identifiers and superblocks. And with RAID on top of the SSDs with FTP, each RAID shard must get a unique FTP identifier and superblock. So the total number of NAND blocks involved is actually the RAID stripe width times the superblock width. This negates some of the locality benefits of FTP, as the goal was to minimize the spread of writes across NAND blocks. Cross-drive RAID in the FTL does not have this problem, as it collapses these layers. So the HFTL RAID stripe is just one NAND block per RAID shard. And the total number of NAND blocks is then just the RAID stripe width, not the RAID stripe width times the superblock width. As a result, the overwrite locality is improved thanks to the broader context. And with FTP, there's still a per-drive FTL. So FTP SSDs have all the scaling challenges and storage efficiency overheads of traditional SSDs. Mandatory DRAM, predetermined IU sizes, read, modify, write, over-provisioning, RAID overhead, those all still apply. They don't go away because they're fundamental to a per-drive FTL, and FTP requires an FTL as it's controlling the FTL. So DFMs and the HFTL are not just designed as individual products, they're designed to optimize the entire system. And it all adds up to layers of compounding benefits at hyperscale. Let's wrap it up with a view of the advantages of DFMs and the HFTL in the context of a hyperscale data storage system. It starts with the efficient use of hardware. DFMs are available in larger capacities, require less DRAM, and scale more efficiently than traditional SSDs. Additionally, the storage overhead is lower with intrinsic cross-drive RAID. The hardware efficiencies are amplified by configurable software with the HFTL. Direct volumes segregate independent workloads, lowering WAF and improving sustained performance. And per volume IU sizes enable bulk data to use minimal DRAM while also handling smaller writes without read modify write. And all scaling linearly without forcing trade-offs when scaling. Aggregate efficiency isn't the only benefit, though, as configurability also enables handling extreme workloads, such as AI checkpoints with PSLC or large databases needing a small IU size. The net result is a configurable, workload-aware QLC flash data storage system that competes with the performance of TLC for the cost of hard drives and at unprecedented scale. That's it. I want to say thank you to my team, everyone at Pure, and everyone at SNIA. Questions? I'll start in the front here.
Thanks. Good talk. Two questions. So it seems like for this one, you get the benefits from knowing your workload coming in. You know that some chunk is going to significantly need like larger objects that you would configure it that way. That's correct?
The benefits you get the question is you get the benefit by knowing something about the workload ahead of time and configuring it accordingly. Yes, I mean you get a lot of the benefits from that. There are some benefits that you get from a purely architectural perspective, like the cross-drive RAID, but to really truly get all of the benefits, you need to optimize it for the workload in some way, shape, or form. Some of those things are easier than others, but yeah. The second question.
The second one is some of this technology also like in your kind of core enterprise storage solution?
Question is this in our core enterprise solutions? Yes. The overwhelming majority of it is in our core enterprise solutions. There are differences, but yes.
When you go to PSLC, obviously you have more space, but you get performance out of that, and you change the RAID levels, you change your provisioning to that, so I mean, there's savings there. But is that programmatically assigned the same rate to direct volume, or do you have to say you need to up the performance and will convert the volume to PSLC?
Yeah.
And is it automated? Is it tiered? Is it
Yeah.
back and forth?
Okay, question is basically more details on PSLC. When do you do it? How much space do you lose? Well, is it automatic? Is it tiered? How does it work, right? The answer is yes. You can kind of do all the above. The simplest thing to do right, is to configure it on a per die basis, on a per die per drive. And now, obviously, the customer doesn't see that; they see a capacity percentage, right? They don't actually see the they don't have to deal with the dies. We do that at the format time, the time of creating the volume. Now, obviously, you can reset the system and format again if your workload changes significantly, but that's the easiest way to do it so that capacity is not in flux. And then there's an open question there of, do you tier it out to QLC or do you let it die in PSLC? Or do you let so then the third option there is, do you let the customer tier it out? So sometimes the customer knows, thank you, the lifetime. If they have very few objects that have a longer lifetime and most of them are going to die, it's actually easiest for them to just copy it out. And then they control it, and they might, when they copy it out, they might not even want it in QLC. That might be their gold standard that they want to move on to 5 other different things anyway. You can tier it out internally, but you might lack some of the context. You can do some sort of accelerated commands to say, sort of copy this from this volume to this volume without actually doing all of the work. But all of them are different options. There's different trade-offs. There's a lot of questions. Yeah. No, it's fine. I just mean in general. Yeah, go ahead.
So anything any of this you can use to optimize rebuild time, both for a particular SSD space within a node and the whole node space, assuming these are local SSDs.
Question is, anything you can do to optimize rebuild time? Yes, our rebuild is incredibly fast. So we've I would say for the past 8 years that I've worked on DFMs, which is as long as they've been around, it's pretty much always been that it takes 1 day to rebuild a drive locally. And that's at whatever the largest capacity is. And that really hasn't changed that much. And a day sounds like a long time, but if you're talking about 300 terabytes, it's not that bad.
Nothing specifically from userspace that you guys use for that. Maybe you can make use of larger IUs, be more efficient and get more throughput.
Yeah, I mean, if any system can be well pipelined. The question is it specific to host-based FTL? I mean, any system can be well pipelined to read, but when you know exactly where the data is on NAND, you don't have to create massive queues to saturate it, right? You know exactly which blocks to read from, and you can have good control over that. Question?
You talked about the read latency that there's a failure on the NAND. Typically, NAND has but now you have to go all the way up to stack and come down for the next step.
No, the question is read latency when there's a failure on the NAND. No, so we have this firmware running on these that's doing all the sort of typical things that an SSD would do for very local ECC. There's not local RAID within it, but you have LDPC and all that sort of stuff happening within the drive as well. Question?
Is the object storage software aware of the host-based SSL?
Is that?
And the second one is, did you explain that regular SSDs are running RAID internally in the SSD?
2 questions. I'll repeat one and answer it as I go. Okay, so the first one is the object store software aware of the host-based FTL? Yes and no. So whoever is configuring the node, which is they're doing it sort of at broader scale, right, is aware of the configuration. But the object storage software is just seeing a standard block storage interface. So it doesn't really need to differentiate its runtime from whether it's an SSD or a virtualized block device. But obviously someone is aware to do the configuration to say that this volume should have this, or this set of volume should have this IU size, and this other set of volume should have this other IU size. We also have a lot of standardized options for that, so you don't really have to hand roll anything. But if you want to make the customizations, obviously you have to be aware that the software is running. The second question, I'm going to.
Were you saying that traditional SSDs are doing internal RAID?
The question is, are traditional SSDs doing internal RAID? So that is my best understanding. I have not worked on the firmware within a traditional SSD, but it is my best understanding that QLC SSDs specifically, from at least some QLC SSDs, are doing internal RAID. There are folks here that work on QLC SSDs that may or may not be able to confirm that for you outside of this room. Ben.
Yeah, I think it was obvious that it's compressible, but you host a 300 terabyte drive, which means that was pretty cool. What form factor is that?
Ben, why would you ask me a hardware question? I'm a software guy. I don't know the answers to that. No, literally no comment. I'm going to butcher it. I'm going to get it wrong, so I'm not going to answer. Question?
So, when you put the QLC into your core enterprise system, do you target it for the primary storage, which is where QLC dominant?
The question is, do we target QLC for primary storage in our enterprise products? I mean, we sell them and characterize the performance and offer the performance characteristics, and it's a pretty gray line. To the end user, it's the end user's decision, right? If they want to put something that's slightly higher latency and lower throughput and larger capacity in as primary storage, by all means, yes.
But the answer is generally no.
Generally no, Randy says, yes. So the question is DRAM savings in the drive versus DRAM and CPU cost in the host, and how do you weigh that? I don't have a great answer, but it's not that simple either. The software stack is incredibly light. The zero copy stack means it's very little CPU cost per I/O, so it's pretty marginal in the overall system. The second aspect is DRAM cost savings on the drive is part of the factor, right? The other factor is DRAM takes up a large amount of space on the drive, so that limits the capacity, takes up a large amount of power on the drive, so that limits the performance, and it's just fundamentally preventing further scale at a certain point, right? So it's all of the above. If it were one line item, right, it'd be a lot simpler to explain, but unfortunately it's not. Thought. The question is, do we lose out on performance from the use of the host software in the same path? We run pretty close to the saturate. We can pretty much saturate the PCI and saturate the drives. Yeah. Yeah. So the question is vendor lock. So you are locked to Pure Storage if you start buying these Pure Storage products, right? No one else makes something exactly like this. But we use multiple NAND vendors behind the scenes within the DFMs, and we've been doing that for a long time. So you're not vendor locked on NAND. Dan? The question is, the advantage to the DFM is improved reliability. Yes, I don't have the exact numbers, but our AFRs are generally very, very, very low on these drives. And that's sort of just what my hardware team tells me. Okay, I think we're out of time, and I think we're out of questions.